Hello, everyone. I'm Jamie Peterson, Director of Wolfram U. It's my pleasure to welcome you to the first session in our new in 14.1 webinar series. Today, we're pleased to have as a presenter Jon McLoone, Director of Technical Communication and Strategy with Wolfram Research Europe, who will be sharing an overview of what's new in version 14.1 of Wolfram Language and Mathematica. Over the next 5 Wednesdays, we'll be bringing you impressive roster of Wolfram developers to present webinars in their areas of specialty. Version 14.1 brings some long requested features and additions to the language. There are about 89 completely new functions along with updates and bug fixes, which is pretty impressive for a 0.1 release. Possibly the first thing you've noticed about the new release is a unified Wolfram app with a simplified installer for all supported products. You just go to the Wolfram Download Center to download the app and activate your Wolfram products. We'll push out a link to the Download Center with you now, so you can check that out for yourself. Click on the Learn More link here to see a community post with more details, and it also has links to helpful tech notes like these for upgrading to the new version. I wanted to share with you Stephen Wolfram's release announcement. Stephen also always gives a really extensive and complete overview of the version of the new release, and it talks about his long-term vision for bringing computational language and computational knowledge to everything. He says today that mission is even more important than ever, supporting not only human users, but also rapidly proliferating AI users who are beginning to be able to routinely make even broader and deeper use of our technology than humans. The model that's emerging is one that uses AI as a linguistic interface where you can use chat to clarify your ideas and then have the LLM turn that into Wolfram language code, where you can see the input and output and do precise computation. Stephen's blog talks about some of the new LLM functionality, and Jon will also have some things to say about support for AI and LLMs during his talk today. In our final webinar in this series, we'll go into even greater detail about specific functionality. To try the examples from today's presentation, you'll want to access version 14.1, and we'll share a free trial offer with you so you can get started right away. I'm going to ask a poll question to the webinar audience now about whether you've already upgraded to version 14.1. We have a YouTube live stream audience as well. And for those of you on YouTube, please feel free to type your responses, comments, and questions in the chat there. We'll have webinar staff and Wolfram technical staff joining us behind the scenes today to help us coordinate Q&A between the webinar and the live stream. So I encourage you to type your questions as we go along. Our staff will answer what we can in typed responses to you, and we'll save some questions for Jon to address at the end of his presentation. So let's see if I've got the polls going here. I'm taking a look at those responses. Yep, they're coming in. Awesome. Oh, a good number have already upgraded. That's fantastic. Thank you for responding to that. I just wanted to note if you're having any problems or have issues with migrating your old files and settings to the new app, we do have some Wolfram support staff here with us behind the scenes. Andrew, one of our support engineers, is here, and if you type in the Q&A, Andrew will try to assist you and have some resources to assist you with. So a download for the webinar presentation notebook is in the sticky note, I believe, in the chat. Let me just confirm that's true. Yep, it says download today's handout. It's kind of in a green background, and that's where you can find Jon's presentation notebook for you to refer to later or even follow along. So thank you for your attention. I hope I'll see you next week as we continue the series. I'll close out for now, but without further delay, I'll introduce Jon McLoone with our featured overview presentation. Jon?
Thank you very much, Jamie. Okay, so as Jamie said, I'm not going to go into the kind of depth that the later talks will. I'm going to try and give you a broad overview, more similar to Stephen Wolfram's blog, but the order and the things I'm interested in and think are kind of interesting about this release don't quite line up, Stephen. So there is value in both, hopefully. So let's get the screen sharing here, and here we go. And let's get started. So it's going to be quite a pacey run through here because there's quite a lot to talk about in the next hour. The headlines are that there's apparently 89 completely new functions, but I think that number really sort of undervalues what's gone on here, because a lot of the time the value is in finding new functionality or improvements that don't require new functions, so that you don't have to learn new things, things that just get better or can do have new capabilities. And there's a lot of those as well. Some of those are performance improvements. Some of them that I'm particularly like are improvements in internal consistency, because in the end, the goal of the Wolfram language is to have an all-in-one platform for all kinds of technical computing. And so we don't want that just to be a toolbox of random functions. We want things to be able to work together, because then you actually get greater than the sum of the parts. And there's also some new external integrations as well for fitting with the outside world. There isn't a headline area of focus because with our goal of trying to provide support for all of the technical computing, regardless of whether you're a scientist or an engineer or financial analyst or other sort of technical professional, we want to have something that's a broader audience, and we've got, I think, things for everyone in this audience. So there are improvements really across quite a range of the Wolfram functionality. So by way of organization, I've ordered things in this from the kind of most general towards things that are more sort of domain specific. And there's nothing more general than the notebook interface. Most of our users who are not using IDEs like Visual Studio Code or IntelliJ to write their code are writing in Wolfram notebooks. So most of you will see the changes here very easily. And I've collected a few of these. The first one, like a lot of user interface functionality, is kind of minor, but at the same time profound, because it makes life easier while requiring no effort to invoke. And this, for me, has been the number one, even though it's very small, the number one feature for writing code is that when you've got large blocks of code and you say, okay, we've got G1 as a random graph, where do I use that? Well, now whenever you click on a symbol in a block of code within a cell in the notebook, all the other occurrences immediately light up. So what's GRP and where is it used? Well, it's assigned here and it gets used over here. And we can see immediately just by clicking on these things, the automatic light up of the uses of the functions. So really just brings the eye right to where it's needed very easily, and zero effort to make use of. The next one is a little bit more complicated story to tell. I'm going to start a fresh notebooks here to explain this. And on Windows, the magnification bar is in a different place. I'm used to Mac. Here we go. Let's make that bigger. So we've had this notion for a long time that you can build up calculations. And so let's say we've done 2 calculations here. And the next calculation is dependent on the previous result. So I would say something like % plus 1 in order to add 1 to that previous result 6. Everyone who works in the notebook probably knows this. Very convenient for just being able to quickly say that last answer and do something with it. And there's extended notation where % means 2 answers ago, and so on. It's got a flaw which can lead to notebooks that aren't a true representation or a reusable representation of what's happened. And as a simple example, if I reevaluate this last answer here, well, when I say %, I mean the last answer. Well, when I wrote it, I meant the 6. But now the last answer is the 7, even though it's below it in the notebook. So when I run % plus 1 again, it's now the non-existent 7 that refers to. So when I open this notebook again in future, this is not a true representation of what will happen. In a fresh session, we'll get 4, 6, and 7, and the source of this 8 is lost. But we have a new mechanism, and you just actually saw it, but it went by too fast to notice. So let's just delete this and start again. I'm going to type % again, but this time I'm just going to pause and let you see what pops up automatically. Now I can carry on and doing what I did before by just typing % plus 1 or whatever to do the calculation. But instead here, I'm going to now reach over and choose which of these results am I talking about that are in this notebook. Do I mean the answer 7, which is an 8, or do I mean the 6 or the 4? Well, let's say the 6. So now we've got something that's like And you'll see now it's slightly smarter in that when I mouse over it, the thing it's referring to lights up, so we can see what we're talking about. And I can do the same kind of thing and do +1 and get 7. But this now is no longer, is still pointing to that cell, not to the history, the sequence of calculations. If I reevaluate this again, then we get the same answer every time. And even if I put something in between here, let's say, let's have 55 plus 55 in the middle here, and I reevaluate this, it still points to the same thing. So it's now a positional reference rather than a chronological reference. And all I had to do was just pause for a moment and use the mouse or the arrow keys to be able to select it. It has a whole bunch of other features, like I can convert it to the actual verbatim thing. I can roll it up with the previous inputs. I can iconize the things and put all of the code in here in an icon. But the basic idea here is we've got a positional reference. And when I save this and reopen it, it will continue to refer to that position in the notebook, not to, regardless of whether it was out5 that created it. So it's a very nice, elegant, almost invisible mechanism for being able to refer to last answers in a more robust and persistent way. Minor things like entities that have typeset forms. These now, we always had the mouse over tooltip where you can see exactly what kind of entity this is, but what are the properties of a city entity? Well, now this is hooked up to the help system, so that for every entity you can get the documentation on the kinds of properties that this particular object has, what it represents, what its subclasses are, and so on, just automatically hooked up in the interface. The next one is also kind of interesting for being quite subtle in its benefit. For a long time, we've had natural language input. Like if I wanted that city, I can do control equals and type London. And excuse me. And when I mouse out, we get some kind of completion where it says, okay, we're assuming you mean a city, and we're assuming you mean the one in the United Kingdom. Perhaps you mean one of the other Londons or a different kind of meaning of London. And then I can accept that as an entity. Again, very nice. The disambiguation, you need a point and click interface to be able to cope with. But in terms of using this thing as code, we've lost two things. One is we've lost what I actually typed. So sometimes that might be valuable to record in the record. And the other thing is this thing only exists in this two-dimensional typeset structure, or it exists in a long form disambiguated form. And we needed the mouse to be able to interact with that disambiguation and control equals those kind of keyboard shortcuts. So there's this new notation, equal square brackets, that is now a text form of inline Wolfram Alpha interpretation. So now we've got a text that I can paste into an email that will work in a text-based IDE like VS Code, and it behaves exactly as if I did control equals type 1 ounce, moused out, clicked accept, plus control equals 10.7 milligrams, moused out and clicked accept. But it's preserving it in text notation. And that works across all of those things that you can do through natural language. So here's the equivalent of doing that lookup of London that I did a moment ago. Now, the next one is sort of a kernel function, not a notebook thing, but it presents itself as an interface. So I've grouped it here. And it's a fairly general and quite nice diff functionality. So at its simplest, I can give it two expressions of certain kinds, and it can give me now a little visual presentation of what's changed. Red for deletes, greens for additions, and there's various different choices of the interface. Like I can see the before and after marked up, or I could see this as a side-by-side view, more like an IDE editor. Where this becomes really powerful is when we've got documents. So I can use that diff on some notebooks objects or some notebook files. So here I've got a couple of examples I prepared earlier. Hopefully I had saved them in the right place. Here we go. So here's the diff object. I don't want the summary box. Let's have a look at the side-by-side. And you can see here that it's gone through that notebook, and I've got a section, a title and section, and some text. But the second version had some extra text added, and the first version had some text removed. And we can see that this something's changed in this. There's been some edit. Now here I can see that I've italicized the two, but there's a sort of more detailed view here, which is a unified. Nope, sorry, it's not the unified summary I want. It's the report. So the report gives me a full breakdown that allows me to go into that particular section cell and see the highlighted, actually exactly what changed in that cell was the italicization, and there's details on the cell options that were added and removed. So everything is available to that diff in a really nice interface. It does three-way diffs, and there is a mechanism for being able to merge diffs or copy diffs over from objects as well. So everything's programmatic as well as being an interface. And yeah, already I found that useful, where I went and took our document quality assurance person's edits and wrote them up, not realizing that they'd actually changed the document, and a quick diff and merge, and I managed to copy over our quality team's edits into my talk notebook, that along with the edits I'd made since then. So very useful stuff for being able to manage document contents. Jamie also mentioned the unified app. At this point, this is about our investment in infrastructure and being able to help us to build variants on products more easily. But in the short term, this will give you the, particularly if you're a site admin, the ability to have a single download, even if you've got multiple different Wolfram products like Notebook Edition or Wolfram Alpha Notebook Edition or Mathematica or Wolfram One. They're all now the same actual downloadable, and they configure themselves on installation to the product that you want. Okay, the next thing that's quite upfront for a lot of people is our work with generative AI. Before I show you the new features, I want to just kind of take a step back and say, what is our attitude to generative AI? And really, this is my kind of view on what we're trying to do, which is we're not a generative AI company. We're not really in the business of trying to make new LLMs. We see that as just another kind of computation. So we've got this 35-odd-year history of building out computation, symbolic AI, and we want to bring out the ability to use the generative AI world and the symbolic AI world together in order to get the best of hybrid solutions. And part of that is also thinking about how humans interact with that. So we're trying to focus on this middle ground that is the best of all of these things. So you won't see in the near future us coming out with completely new models. We're going to leave that to the likes of OpenAI and Anthropic and the like to work on. But it's a useful bit of computation. So let's look at what we've been doing. Because we're not trying to do LLMs themselves, we're trying to be back-end LLM agnostic. So just like when I solve a differential equation, I've got a dozen algorithms to choose from, we want that to be the attitude to large language models. So all of our commands have been things like LLM synthesize, not ChatGPT synthesize. And we've massively broadened now the range of built-in LLMs that you can choose from. This is the current list that's built in. We also have some code that's not in product for Azure private OpenAI as a backend model. And each of these have dozens of models to choose from, some of them. So you can switch between them. You can do a parallel computation where you ask all of them to answer the question and combine the results. You could ask one LLM to mock or critique the response of another. You could just switch backends after you've written some code because some great new model comes out. We're trying to make it so that's a last minute detail to say, oh, actually, I wrote this code for OpenAI, but I hear the new model from Google Gemini is even better. Let's see if my code works better. And you don't have to rewrite the code. It's a common interface to all of these different LLMs. Now, partly to make it easier to use one of the uses of LLM. So in our world, you can use them for words, but you can also use them to synthesize Wolfram language code to help you write code using our chat notebook. And to make that easier to understand the relative benefits, we are maintaining now, I think it's a weekly update on the latest models and their performance on Wolfram language code. So you can see, as of today at least, the winner for getting the correct functionality for Wolfram language code is Meta. So we have a big benchmark, and in half the cases, it can write absolutely correct, ready to run Wolfram language code. And in 99.7% of cases, it can write syntactically correct code, but it hallucinates a command that we don't have, which is still already useful because sometimes it's easy to correct, or you can say there's no such thing as that command and it rethinks. But out of the box, it's getting about half the time it can meet our coding challenges totally synthetically. And this even covers things like local LLM models like Falcon LLM, which does very poorly in code, but is still useful sometimes for other tasks. So another infrastructure difference is that we are now also generally supporting multimodal models where the backend accepts them. So some of these models that are provided are text only, but some of them are multimodal, and we now support that in a system agnostic way. So I can ask for a synthesis of some text, and I can give it some prompting and some more prompting and an image, and I'm telling it to use, in this case, OpenAI's GPT-4 Vision Preview, and hopefully it will take all those 3 bits of information into account to say, yes, I appear to be holding up 3 fingers. Now, as well as being seamless between different AI models, we also want this kind of functionality to be seamless between code interfaces and the kind of the way that we package things up for humans. So if I switch now to a chat notebook, then let's make this a bit bigger. Then chat notebooks also now support multimodal as well. So I can, try that again. I can get the keystroke right. I can type in what is in this picture and paste a picture into the input, and we'll get the same kind of effect that we had before. So the notebooks, our ability with notebooks to be able to seamlessly handle all kinds of content has made it kind of easy for us to have user interfaces that now can seamlessly mix inputs. I guess I prepared this one before at home, but also making these things join up. Part of our story of joining up LLM world and the computational world is to provide LLMs as a kind of computation, but also to provide computation as a resource for LLMs. And so we have this LLM tool capability that allows you to teach an LLM to ask Wolfram either by writing code or by sending some values to a predefined piece of code for the computational answer, which it then uses within the chat. So I've created a specific persona for this notebook to show that that also joins up with this multimodal world. So I could say, for example, describe what you see. Oh, I misspelled describe, but I hope it'll figure it out. And in this particular persona, I've taught it that it's allowed to use the camera. So it's now going to my webcam and it's grabbing a picture of me right now, which just looking at what I'm seeing on the other camera, looks like that's a perfectly good description. A person sitting in front of a bookshelf wearing glasses, yep, in a striped shirt. So that's used the actual query from the camera and what it actually did, which was to go to the tool and query it with current view, and came back with an image from the camera, which are then used in the multimodal LLM to be able to answer the question. Now, the next thing that we've got is we're trying to also extend the paradigms by which you interact with controlling LLMs. So for those of you who don't know, there's basically 2 ways to make the LLMs do what you want. One is with what's called RAG, Retrieval Augmented Generation. That's tools. So that's the kind of thing I just showed you, where I gave it the tool of being able to look at the web camera. And anything we can do in the Wolfram language can be a tool. And the other way you can control them is through prompt engineering. You tell it things in words. You say, you are a chatbot, don't swear, talk about our product, but don't talk about competitors. I know, whatever the things you are, to describe a scenario. And we've now added some paradigms for dynamic prompt engineering. So we're trying to have a language that if you want to chain together LLM requests, control them, make them do certain things, feed that into user interfaces, all of that joins up. And this is a step in that. So I've got a very toy example here, which I'll explain, which is I've got a prompt generator that is going to be the prompt engineering for my persona. But instead of saying that up front as some static prompts to say, be friendly and nice, answer questions succinctly, and so on, I've said instead I'm going to compute those prompts. And here I'm just going to give it a single prompt, answer using only blah words, where blah is computed at the moment that it needs to talk to me. And I'm going to compute it by counting the number of messages, the length of the messages of the current chat, and divided by 2 in rounding. So this will become answer using only 1 word. And the next time I talk to it, it'll, let's say, answer using only 2 words. So I've created a chat persona that will answer in longer and longer answers each time I talk to it. Not a very useful persona, but the simplest thing I could think of where you could see it actually in action. So now if I set that chat conversation up with our representation of a symbolic chat, and now I can say, what is a cat? And we will get an answer when the OpenAI, which is my chosen backend, answers. And you'll see here that it's answered in 1 word, but if I continue the conversation, I'm just going to ask the same question again. The conversation, what is a cat? Feline. What is a cat? Domesticated feline. If I ask the question again, it's gone on to a 3-word answer. So without having to massage the chat object each time, we're running some code that updates the prompting to tell the LLM how to behave. So why is this useful? Well, if you can imagine, instead of this sort of 3-token program that I wrote here, you had something that, let's say we got a student conversation teaching English, and as we're talking, we're getting scoring on the quality of the English that the person's using, and we're getting a lookup from the database to see what else do we know about this person, and maybe we're looking in the database to see those scores changing. We could be dynamically prompting it to up the complexity of the language or simplify the language to match the conversation it's having based on computed values, like have you answered the question? Have you used a future and past tense verb? Can we trigger the conversation to test those things by constantly dynamically scoring what's going on and adjusting how the LLM behaves, rather than having to say all of that as an upfront definition. So it's a powerful paradigm wrapped up in basically 1 command in the Wolfram language. Right, let's move away from AI down a level below. AI, of course, is all basically machine learning in the background, and we provide a lot of tools for allowing people to do their own machine learning type tasks, build their own models. And one common paradigm, which actually comes up a lot with providing knowledge to LLMs as well, is vector databases. I'm going to do this slightly backwards because I think it's easier to understand if we look at semantic search, which is built on top of vector databases. And we have basically a very simple mechanism for building indexes that are semantic. So here I've got a database of facts about animals. And I'm just going to quickly build a semantic index, search index for those facts. And so you can see single command here. We've built an index. I can deploy this in the cloud if I wanted to share the index with you. I could, obviously I would wrap it behind some user interface or some code, but this basically represents a vector database of the semantic meaning vectors of the words, and it goes nicely with this command semantic search that says, for a given index, I'm interested in canines. Give me just 1 response from the database. So even though the word canines doesn't appear in my database, the semantic nature of it knows that dogs are the nearest word to canines, and so this is the search result that it's come back with. And this is a scalable thing for very large quantities of these vectors. A typical thing for that is in kind of knowledge retrieval is you index all your big folder of PDFs that you have to be able to find the right document quickly as search, and then you might use either computational import to do something with it to extract facts, or you might use an LLM on it to interact with the document. And that automatically works over things like notebooks. So if I'm not going to run this code now, it takes a little while to run. I ran this over all of the notebooks, all of the files of type notebook in my personal writing database. You can see here that I've got, actually, I'm not sure that I have installed this correctly on this machine, since I wrote this on my own machine. Oh, no, there we go. It just hadn't refreshed in the notebook. So there's an index of 27,000 items from 255 sources. And now I can say, right, let's do a search for anything I've written about bistro meals, find the first one of those things, and open the document. So it's a kind of quick way of saying search and open. And now it's found my blog that I wrote some years ago on unhygienic food. So I don't know if the word bistro appears, but I talk about cafes and restaurants, and I did some analysis here of the food hygiene data set in the UK some time ago. Now, again, we want everything to join up. So if I just switch now quickly to the same thing hidden behind a chat notebook interface, then the idea of having multiple tools starts to become kind of interesting. So I can use that as a semantic search thing to say, find a document about word games. I've already taught this persona that it has the ability to use a tool, and LLMs are a little tricksy sometimes, and it's decided to disobey me. I'm just going to be a bit more explicit here. Have I actually? I may have installed the wrong tool here. Okay, let's skip that one. I think I installed a version of the tool before I had semantic databases. I put the wrong one on this machine. But what it can do is it can then access the semantic database, find the thing, and then I can say read the documents and give me answers. But I've got the old version of the tool. Sorry for that mistake. So the underlying mechanism, as I said, is a database for vectors. So you can also roll up your sleeves and use that in any way you want. So here's me doing the same kind of thing, but for images, but taking control of all of the steps. So I've got some images, and I'm going to go to the Wolfram neural net repository and fetch a model that is trained on image recognition, but I've done a net drop to say I only want the last layer that has actually some vectors in it, and put those vectors into a database. So it's the same kind of thing, but I've got here now 6 vectors that represent the features of those images. And then I can repeat the process by saying, find the matches that have similar semantic vectors to this image, and we find the images it considers the closest match. So I had squirrels and monkeys in the data set. I gave it a picture of a monkey, and it found me monkeys. Right, on to some other things. We've had things like classify and predict, and net train for doing machine learning models yourself. We've had for quite a while support for GPUs, but only support for CUDA up to now. And in this release, we're adding Core ML and Direct ML support. So CUDA is the proprietary language for interacting with NVIDIA GPUs. They are the biggest company in the world for doing GPUs, but they're not the only ones. And in particular, this particular timing here, I ran on my own personal Mac. We've not had Mac support for GPU before, but I think it's Core ML is the Mac technology that we can use. So now we're getting GPU acceleration on the Mac, and this is just using one of our repository models, net model. Takes what is that, a 30th of a second to identify that as a tiger, but it's about 10 times faster if I add target device goes to GPU and run that using the GPU hardware, not the CPU hardware. And so there's been improvements to things like NetChain and NetGraph to try and make that something that can generally be benefited from in both training and execution. Not strictly machine learning, but I kind of think it's fundamentally the same thing. We've had regression for an awful long time, since probably the first version of Mathematica, where I can take data such as these 4 numbers and say, let's fit a linear model to that, and x minus 2 is our best fit model. We're always trying to make the system join up better. So for a while, we've had uncertainty, error bounds that are a representation of a number with a uncertainty interval on it. And now we've added that support for that in the last few versions. So since about version 12, we've been making sure all of the functions like mod and sine all do sensible things with intervals and uncertainty. We're now adding that to higher level functions. So now when I do the same data, the numbers are all the same, 0.8, 0.2, but the errors are different. So I've added more uncertainty on this final number. Maybe the experiment that I got it from was a less reliable piece of equipment or something, and fit to that same numbers but different uncertainty. It now takes into account the uncertainty in the values to give me a different fit. And if we look at that visually, you can see what's going on here. The blue line is the old fit that we had, which does its best to get as close as it can to all 4 numbers. But once we tell it that there's a lot of uncertainty in the 4th number, then the orange line has been allowed to be a bit more relaxed about being near that 4th number. It wants to make sure it maintains it's within the error bounds if it can. and it's clearly within the uncertainty interval of that number. But now it's on average closer to the other numbers by allowing it to be more relaxed about this one. And we also have the same if you have uncertainty on the input, on the independent variable. So we can have both independent and dependent variables having uncertainty and mixed levels of uncertainty, and have it compute the correct weighting for the points to generate the most appropriate plot. Yet again, we've got some improvements both in performance and coverage of ONNX support, which is the main neural network interchange format. Right, let's go on to something a bit deeper now, a bit more maths here. I decided there's a bunch of things that could broadly be put under calculus, but there's some fairly different things going on here. The first one is very much a physics, electrical engineering kind of world. We have for quite a while now had a really decent partial differential equation finite element system for being able to model physical things like electromagnetism. And in more recent years, we've been adding a layer of language on top of that that allows you to talk about physical and multi-physics problems at a high level rather than having to get down into crafting the correct PDE representation. And that's grown a little bit further. The new thing here is electric potential, electric current PDE component, and I think electric potential condition might also be new, but this is definitely new. And the idea is here that we're modeling electrical currents flowing through materials. So I've got some geometry represented using our geometry framework. So that could have been imported from a STL file or from a CAD package. I'm using our entities to prescribe the materials of that, to say it's tungsten. So some of these things depend on properties like conductivity. And by telling it tungsten, it can look up all of those values. And then we set up some boundary conditions, electricity flowing in at one end and out the other. And then we're solving it and visualizing the current density on the thing. And you get here from our slice plot 3D, we can see now that we get really constant current in the straight lines, but as it goes around corners, you get a greater current density on the inside of the curve, that the electricity is kind of trying to shortcut around, and so you get some unevenness in the density. But all of that is basically the solution to a PDE behind the scenes. So that language now covers all kinds of things like physical stresses and strains, electrical components, fluid flows, mass transfer type problems, and I think I'm missing a class, but my mind's gone blank. Okay, getting a little bit more into the ODE world, we've been able to compute all kinds of ODE type and delay differential equations, all these kinds of differential equations, but we're now trying to move into more interesting properties of those. So if you consider this flow that's going on here, that perhaps this is some kind of electromagnetic field, or it's a fluid flow or something. You can imagine here that if I released some particle into this flow at -1, then it would, as time progresses, as we move right, it would flow down until it reached -3, and then it would stop. So if we inject something at exactly -3 or exactly 0, then we're at a fixed point within that differential equation. Finding those fixed points is now covered within the system. So I can say the fixed points of the differential equation that represents that flow, and we get the two fixed point values for the inputs of -3 and 0. But also, if you look at the plot here, they're slightly different. If we were slightly away from -3, we would flow back towards it. If we're slightly away from 0, we flow away from it. So one of these is stable, and the other one is unstable. And we also have the ability to do that as well. So we can find both the fixed points, but we can also attach to them their stability, that the -3 is the stable solution, and 0 is a fixed point, but it's an unstable one. So any perturbation, then you're going to travel away from it. Now, the next one is getting a little bit more theoretical, and this is possibly one of the most asked for features on this list, that we've had a great framework for being able to work with matrices and arrays, all kinds of functionality. And we've been able to work with matrices and arrays with symbolic entries. So I can have a matrix A, B, C, D and say what's the determinants of that matrix, or the eigenvalues of that matrix, and it's quite happy with those symbolic values. But we've never had a representation of the matrix itself as a symbolic value, we've always had to populate the matrix and then work with those symbols, and that's both computationally much more demanding, but it also ends up with solutions that are basically unusable, that they might be technically correct, but they're not in a form that you can make use of. So now, for the first time, we're introducing a matrix symbol that allows me to declare a symbol M as being a matrix that is, in this case, 7 by 7 in size. And it doesn't do anything. It's just a symbolic wrapper to allow me to say this thing is a 7 by 7 matrix. And this also works for arbitrary tensor arrays as well. So it could be 7 by 7 by 7 by 7. But now that we've declared that, all of these functions in the list above can now work with those symbolic objects. So, for example, if I ask for the derivative or the third derivative of the matrix of the determinant of M with respect to the matrix M, then we can get that out in terms of that matrix. And we've got some kind of rich tensor notation here for things where there are calculations according to the indices of the tensor. But we've got a kind of high-level symbolic representation of those operations. So this is useful if you're doing things like stability type calculations of working a system through a set of steps and be able to understand what would perturbations on that be. Or some of these things we could then, as the final step, normalize them to turn them back into actual matrices of numbers or symbols and pick out individual elements as a final step, not as a working step. A very minor bit of syntax, but you can never underestimate how much of a pain it is when little things get in the way. This is the symbolic notation we've had for a long time for solving differential equations, where we've got the derivative of y as a function of t, but very often in textbooks, the kind of time parameterization of the differential equation is omitted as sort of just implied, and we now have the ability to accept that notation without you having to copy things out of a textbook and then go through, keep adding bracket t, bracket t, bracket t all the way through. And we can just give that implicit notation, and it has to invent a variable to be able to represent the solution, but we can work with that as well. So some quite serious bits of maths and mixed in with some nice syntactic improvements. Let's move to another world now, which is geometry. Just a couple of things here. We've got this big framework for geometry, both for doing geometric calculations like what's the area and volume and center of gravity and the like, and can handle all these kinds of objects like we saw in the PDE model. This is just a piece of geometry within this framework. And we've also had the graphics world for a long time, which is more aesthetic, but actually they're tightly related. So first of all, we're still expanding out the geometry functionality. We've had ways of describing things in terms of symbolic objects like the combinations of pyramids and polygons and spheres and the like, and equational ways, but the equational ways have always been in Cartesian coordinates. And we now have a way of being able to describe geometry symbolically in polar coordinates. And because it's symbolic, when I do things like area of that, we'll get symbolic results out here. So we can work out that the exact area of that is 19 pi by 2, but from a very elegant, without having to convert to Cartesian and back again, we can just state geometry in polar coordinates. So really a convenience function, but nevertheless useful if that's your world you work in. We've also joined up some of the aesthetics. So if you're working in things like AR or you want to visualize the geometry you're calculating, you shouldn't have to choose between looking nice and computing computationally. And actually, sometimes it helps just to understand what we're seeing. So here I'm taking two solid geometries and finding the geometric intersection between those, but I've given these aesthetic details and it's preserved that coloring into this geometric thing, which itself we could still compute with. So we're trying to blend those worlds. Geometries that come out of CAD package might have all kinds of interesting coloring information to make them look more realistic, and we don't have to throw that away now when we compute regions or computations across them. Also in the aesthetic space, we're more in the educational space now. We've had this world of Euclidean geometry where we can describe things symbolically as a scene of intersecting circles and lines and whether things are at right angles or can rotate or not, and then being able to work out conjectures that you can conclude for that. But they've always had this single visualization, And it's always nice to be able to make your stuff look nice as well. So if you're teaching with this kind of thing or publishing, then there is now the plot theme mechanism that gives quick, convenient ways of controlling the look of visualizations now applies to the geometric world as well. So there's minimal versions, there's colored versions, there's labeled versions, all at a single plot theme command. I'm not going to show any examples of these because they're just performance, but there's some important bits of computational performance improvements. We did this for numerical solving before, where if you're working with very large systems with thousands or hundreds of thousands of roots, then sometimes you only care about the main, the first 10 largest roots. And so it's much, much faster to be able to compute in a limited way. Solve now supports that for symbolic solutions. So I can say, give me only the first 10 roots of these 1,000 solutions. There's a core algorithm in many of the optimization routines, and minimize gets used in other places as well, like the geometry calculations. Sometimes they're doing minimization internally. And so the Nelder-Mead algorithm, which is a core part of that framework, has now been significantly made faster. And similarly, for very large graphs, our centrality measures have all been revisited and are much, much faster. So things like PageRank centrality and so on, for particularly for things like social network analysis, where you're trying to find the center of influence in networks. Right, let's now start going into more specific domains. We've been building out audiovisual for a long time in the Wolfram language, being able to work with images, audio, with videos, mostly a set of convenience functions for making it easier to work with video here. But the first is just a performance improvement, but I think it's an important one, which is there is a new audio speech recognition. So I've got here the classic JFK, we choose to go to the moon speech. Let's just load that into memory. It's a 27-second speech, and we can transcribe that. But in previous versions of Mathematica, we were transcribing in less than real time. So on a good machine, it might be 1.5 times slow. It might take 45 seconds to transcribe that. I think on my machine, when I was last doing this on decent length text, it was taking 2 to 3 times longer. So it might take 1.5 minutes to transcribe that. The new model is substantially faster. So if I rerun that now on the new model, then hopefully we'll get something back quickly. There's the 30-second transcription. And I think actually that absolute timing took some time to load the model. So if I just run it again, that 6.8 seconds, I suspect will be slightly faster the second time. Or maybe, yeah, that's getting a bit closer. I think I was running this in about 3 seconds before, but I guess I'm running video broadcasting software now that's slowing things down. But 5 is still not only a massive improvement on before, but the crucial thing is it's much faster than real time. So now that starts making speech recognition useful potentially for interfaces where you want to capture speech as it happens and action it straight away. And being able to take a speech request like we do in chat notebooks to say, write me a piece of Mathematica code that does the following. You don't want to then have a huge pause while it processes that and then answers, and you've got these gaps. It can answer, pretty quickly after you've spoken by being able to process that in a fraction of the time. So it's I think crossing a major barrier once you get significantly better than real time. Okay, some convenience functions for video. These are things that you could do with some elaborate programming. So here's a video I've got of some piece of baseball. This particular example is illustrating what happens if you have computations that don't depend just on the now or short interval of a video, but are a kind of cumulative effect video. So we might want to look at the next frame, but include it in something that is being worked on as we move through the image. So image frame fold is the way of doing that. And what I'm doing here is stripping the background from the image and folding that image on top with image composition on top of what we got so far. And the conclusion of that then is this thing that allows me to make a video that is everything you've seen so far in the video up to the point. Another paradigm is video so-reap, an analog for those of you who are Wolfram language users already of the so-reap commands. And the idea here is that very often you're only interested in bits of a video. So I captured this bit of video of me sternly looking at the computer occasionally, smiling. So at some point, hopefully I will smile. And what we're only interested in is the happy moments of the video. So, a classic example of this would be trail cams. You're interested in analyzing creatures in a woodland and you want to leave a camera out for a week. You don't want to look at 7 days of video. You want to capture the bits when a bear went past the camera, and you want to say, give me a video of all the moments that the bear was on camera. So that's what the basic paradigm that So is dealing with. I'm mapping over the video a function that says, if the facial expression is happiness, then sow the video, otherwise move on. And then we'll collect together all the sown bits of video to make a video at the end, and we end up with a video that is just a composite of the smiling bits. I think I smiled twice in that video, and it's thrown the rest away. Another convenience is visualization for quick look at videos. So there's video summary plots that lets me take some piece of video and give me a grab of a bunch of the frames and the audio track in a single image. And like most of our visualizations, there are choices of styles, so I can see the frames not stacked but flat, so we can see them, or I can do some pre-processing and styling. So there's all kinds of ways you can use that, but it's just a quick glance function of a video. Now this one is really, it's one of those things that's minor and you won't notice once you start using it, but I think is crucial to the usability of the Wolfram language, that things just work. And is a lot of the value that you're not having to constantly convert data types from one to another. So now in this release, all audio functions will work directly with video. So I could before have taken a video and do an audio extract from that and then do a spectrogram of the audio. But now all of these functions just work when you say, what's the spectrogram of the sound of that video? And there's the spectrogram. Let's do some machine learning recognition. What's going on in that video, or the audio of that video? And these things just work. And this is the beauty of the Wolfram language, because we know that thing represents a video. We know how automatically to convert that into the audio that this needs, so that all of that automation joins things up. So I can give this sound, a streaming sound reference, an audio stream that is currently playing a video, and all of these things just work automatically. So that goes across quite a lot of functions, but you'll just notice that you don't need to do any work now. And the last paradigm, again, just a convenience for constructing video, but a lot of people use the manipulate command for making interfaces to play with content. So here I've attached a slider to some value in a pie chart. So we've now got an analog command, manipulate video, that takes all the same syntax as manipulate, but makes a video as if you were playing with that. Oh, I haven't actually run that. Let's just, since I switched machines. So if I just build that video now, another little feature here, you get to see all of the video processing commands give you a thumbnail, so you can see the progress and what's going on in those videos. And now we've got a video that I've constructed that does the same thing as playing with the manipulate. And there's all kinds of controls for how you would move through the slider space if there were sliders, to be able to give the route through, in this case, a color picker. So there's a rich syntax there, but it's basically a way of taking things that you've played with as a manipulate and say, I'd want to make a video to present this without having to recode anything. Right. Next, we're going at quite a pace here. So these are notebook features in a way, but I've classed them as a domain-specific thing, as educational assessment. So obviously there's the whole world of education as an industry, universities and schools, where this is central, but this could also be potentially for things like publications, where you want to check your understanding in an ebook, and it can be for things like sort of more industrial corporate training type contexts. And it can also actually be sort of subverted to just information gathering. It's an interface that we have various representations for questions and answers and scoring. Now, one to point out is that we now have a platform that brings together a particular workflow for that. I'm not going to talk about that here because it's not core Wolfram language, but we now have a new solution that is on sale that is a platform for you being able to set up banks of assessments, manage which students are supposed to be doing which assessments when, managing manual marking, and letting you view scores. So the whole workflow of joining up assessments in a customizable and adaptable way. I'm just going to focus on some components that are in the core Wolfram language, so all of you Mathematica users will get the following. So the first thing is we are expanding just the graphic user interface of asking questions. And a good example comparison are these three: select, complete, drag completion, and text completion. because they actually take exactly the same arguments and exactly the same question, but they illustrate that sometimes we want different levels of prompting to ask a question. So this is a multi-part question. So we're asking you to fill in the blanks in this question, and we want you to say Shanghai is in what country and London is what country. So let's fill it in and say France and Spain, and click submit. And it says, no, you've got that wrong. So it's a composite multi-input field question with contextualization of being able to put the input fields in their places to say what goes where and scoring the thing as a whole. But we might want to give more prompting. Maybe that's too hard. We could ask the same question in a way that says, here's 6 candidates. And we've now got a GUI where I can drag the candidates into the fields and then get the question scored. Or I could be even more prompting and say, I'm going to give you separate categories for each thing. So this time it's a pop-up menu, and I have only 3 to choose from, China and England, and click submit, and we get the correct answer. So same question, but different levels of scaffolding to help the student know what they're supposed to do. And of course, we could ask some totally open-ended question and ask them to type input field freeform text. So that's those 3 new interfaces. There's a couple of others that are similar kinds of ideas. There's drag categorize that allows me to put things into categories. So I've got a source zone and a target zone that I could put multiple things into and say, are those all now in the right category? No, they're not. And I could potentially rearrange them if I allow multiple attempts. And if I knew the answer, I could get it right, but I don't. So let's move on. There's click locations, which is an image that is a freeform area, but there are specific target locations. So I can say, in this case, click locate the stoplights, and I can drag the locators onto the 2 stoplights and click submit. And they have a notion of tolerance. How near does this have to be before it's correct? And we have a sorting question type, where I just simply have to put things into order. And as I click and drag these things, we can put them into a different order. It automatically resorts them as I move the thing around. And then, is this in the order of size? No, it's not. And that's on top of, we've got a collection of the standard things like multiple choice and an input field and the like. So we're trying to build out this lexicon of ways to present the question. The separate part of the problem, which was hidden behind the scenes on those, is the scoring side of it. And we've started a journey there to build out assessments that are the more domain specific. So the simplest assessment function, you simply say that 1 is the right answer and 2 is the wrong answer. That's the simplest assessment function. But what I can do is I can also set things up with specific scoring rules, and algebraic value is one of these new ones. So I'm going to compute some solutions to this quadratic equation and set up an assessment function that says, I want the answer to be one of those solutions. But what the same means is according to these algebraic value rules. And this is the assessment function is what's behind the scenes in the, if we go back to one of these, the code behind these questions, then you'll see that there's an assessment function behind the scenes that says what right and wrong answers are, how many points they score if you've got a quiz with with different scoring in it, and so on. So these are the behind the scenes scorings. And the idea of this is that I can give an answer like this, and it says tick, that's a correct answer. But I might have posed the question structured completely differently, that there's an ordering difference, and I didn't write 1, I wrote a half plus a half. But the transformation of adding those 2 numbers together and reordering so it's b plus 1 instead of 1 plus b, those are allowed transformations. And so there's perhaps 1,000, well, it's an infinite number, but there's perhaps a dozen reasonable answers that a student could give to that will all be marked correct. But if I cheat and I try and do some transformation that's not allowed by saying, actually, I'm going to put in some Wolfram language code that says, actually work out the solution for me, and take the first solution, it says, no, that's not an acceptable set of transformations, even though this thing might actually compute to an acceptable answer. And if I put that answer in, oops, I've done the 1, then that would be, if I can get it right, is an acceptable answer. So we're trying to build a whole language of these things where some of these things are very contextual, that at one age in education, the answer might be different than another age. Does the student know about complex numbers? If they're young, the answer is not a solution. If they're older, then the answer is I. And we want to build up, and also those things depend on the educational system, that American standards are different than, say, British GCSE standards. And we want to map out a lot of those and give them named assessment functions. And of course, you can write them yourself. In the end, these named assessment functions translate into some elaborate Wolfram language function that you could craft on your own, but we're trying to build that out for you. Right, let's go to something narrow, and I'll go quickly through because, to be honest, it's a little dull, is dates. Dates are sometimes very important to get right. If you're doing financial calculations, knowing what a month on from January the 29th is kind of important to understand whether there is a February the 29th this year or not. Those kinds of details really matter, but nobody really wants to get involved in writing these things. So we have a big date framework, and there's still things we're doing on that. So the first is a simple convenience, which is conformity. So here I've got two dates that are the same, but they have different granularity. So here I mean the day of, not specifically midnight on that day. And here I mean the minute of. I've got a time object, which is abstractly any day of the year, future and past, but time-wise now. We've got a Jewish calendar and an Islamic calendar reference, and there's all kinds of different calendar systems and date conventions. Conform dates will simply put them into a common date system so that they are immediately computable or can be presented the same way. We've now extended most of the standard statistics functionalities to be able to work with dates directly. So if I do the median of those dates, again, it's one of those just works type problems that you could go through all of those and convert them into, say, absolute time in seconds since 1900, and then work with those numbers and then compute that back to a date. But just having things like median just work on dates is much more convenient. And similarly, we've extended the statistical distribution framework to be able to just work with dates. So we've had things like normal distribution, and indeed 185 odd different distributions are in the system. But now we have a single construct that turns all of those into 185 date distributions. So we can say we've got dates that are normally distributed in days, with the 0 day, the middle day, being this date. That now gives us a symbolic date distribution, and then a lot of the operations you can do with distributions just work. So I can say, let's make a random date from that distribution, or let's make 1,000 random dates and do a date histogram of those distributions. So again, this is a meta distribution that works with distributions like our other meta distributions, like censoring, or largest out of several samples, or copulars, and that combine distributions. They will work with distributions to make new distributions. And this is one function that gives you now a whole world of date-related distributions based on everything that we've built before. And if you're in these sort of computational history or real-world entities, we've extended some of our data built-in data streams to support dated entities more widely. So most notably things like historical geographic entities. So a concept like the Roman Empire is an entity, an object that we can ask questions of, like when did it start, when did it end? But when we ask things like make a map of the Roman Empire, well, that really depends on which Roman Empire we mean. So now that takes dated as a modifier, and we can say, give me a map of the Roman Empire in the year 100. Or compute with things like geographic area of that over time. And so here's the rise and fall of the Roman Empire in land area over a 200-year period from 0 to 200. So little kind of extension for computational history type work. Another very specialist domain, astronomical. We've got a couple of things that we've been adding a lot of astronomy work in the last 3 or 4 releases. So a couple of extras here. We now handle astro axes correctly. So if I ask for some visualization, these axes are now correctly drawn in the various planes of reference of the astronomical system. And why that turns out to be complicated is that we support all kinds of astro projections. So here I'm using the mole-wide projection system, and you can see things like the grid lines and the axes suddenly become exotically differently shaped because of that map projection. So making sure that the axes that the main axes you could choose from are available. You can turn them off individually, you can color them and have them drawn correctly depending on the projection is a reasonably computational piece of work. There's also another minor computational feature, which is astro rise set, which is when will the moon rise from a given location at a given time. And this works for all astronomical bodies. So when will Jupiter rise from a certain location at a certain time? And of course, times are complicated because I mean the time now or the time there, taking into account the speed of light and the calendar system. So there's quite a lot of details, but those are all taken care of. And these things, it turns out, again, are slightly more complicated than you might imagine from the outside. So if I plot this moonrise time from here, even though I'm on a private network, so here is going to mean I think I'm in Champagne. So this is the view from Champagne from now to a year from now, the rise and set times. You can see there's all kinds of periodicities going on that combine to make that kind of a non-trivial calculation, even before you take into account speed of light and where you are in the world. Right, and another domain that is emerging for us, and there's some major new work here, is biomolecules. So we've had biosequence representation for a few versions and all kinds of interesting calculations. So I can make up some random, let's add a little bit of randomness to this, add a SPS to the end of this peptide sequence, and we've been able to do computations on that. But this is a sequence. This is one thing after another. And there are things you can work out about that, but these enzyme type sequences, they fold into elaborate three-dimensional shapes. So we now have a new biomolecule construct. And if I ask for a known sequence, it'll go to a database and fetch out experimentally verified three-dimensional geometry. But here, because I'm giving it a random made-up sequence, we've built into biomolecule a enzyme folding optimization algorithm that tries to predict how that thing would fold into three-dimensional space according to the energy minimization or whatever the other characteristics that describe folding. So it's a standard algorithm. It's not a match for these supercomputers that are trying to do these kind of folding exercises super accurate and at scale, but it allows you to take a random sequence and get a reasonable first estimate of the fold of that. And that then brings new computations we can bring to bear on that. There's various properties we could ask of that, of the coordinates of these things. For example, I can get the sequences of individual fold sequences as the atomic symbols. We can visualize the thing. So here's a plot of how that 3D geometry has ended up as it's all kind of folded up into a tangle. We can find other kinds of calculated visualizations, like rather than showing me the paths, show me the surface that would be accessible to a solvent. So we're going to get a similar three-dimensional geometry, but now we're getting that accessible surface area, which we can convert into a geometry that we can convert with geometry calculations on that, such as what is the surface area of that and so on. And we can also convert between other representations. So here is the stick and ball atom representation using our molecule plot 3D, our molecule representation for the actual atomic structure of that atom by atom rather than peptide by peptide. And again, that has with it its own calculations that we can do on it. So quite a lot of really powerful bio sequencing type calculations now starting to join up to make quite a lot of stuff computable alongside all of the optimization and calculus and things that we've done in the language. Now, I put this one last because depending on who you are, this is either very core or very specialized. The language pervades the whole system, but you can get by without these bits of the language quite happily. So I've put them as specialist, but they are actually very important to the story of the Wolfram language, that the Wolfram language is an interpreted system, which makes it really good for quick coding and interactive use. It comes as a price computationally in terms of performance. So there are languages like C and Julia and the like that are designed to compile and be fast. And what we want is the benefits of the both. So for a while, we've been building out the compiler that takes Wolfram language interpreted code and makes optimized compiled code that runs as basically machine code on your CPU. So we're trying to make that now less of a specialized thing by giving more tools to make it easier to use. One of those is this compiler information command that now allows you to ask questions like, if I want to use the map command, is that a compilable function? And I guess I haven't loaded the compiler yet here, so the compiler takes a few seconds to load. The compiler information command is very fast, but it's loading all of the compiler libraries for the first time. And here are the different, not just, yes, it's compilable, but the various different patterns and types that it knows how to compile. So we can start figuring out what are the types in the compiler, like can I give this a real 64 number? Will it know what to do with that? We've got information on the compiler types themselves and how they relate to other types. We've got information on the built-in data structures and these higher level data structures we provide that are built in the compiler, like hash tables or byte trees and the like. There's information on how those work through the compiler. So it's still somewhat specialized information, but we're trying to make it all less having to read lots of documentation and less trial and error. We've also extended the compiler error generation, and some people think this is an important feature, that the fact that I'm giving it very typed information that the typical Wolfram language doesn't care about allows us to do error detection in a more precise way. And that compiled. That was meant to be an example. Oh, no, sorry, that was an example of something different, which is that, and I'll run this again here, that we now get feedback. And because I've compiled this before, that was a bit too fast. But perhaps you saw while I was talking there that you were getting information on what was going on inside the compiler. So you now get a kind of progress indication as it goes. So it's not just kind of like silence until it finishes. You get some understanding of how far it's got through the process, which commands it's compiled. So just a bit more convenient again to use. This was the example I thought I was doing, which is trying to compile something that will fail. Now, we always got this failure, couldn't find a definition for arg1, but arg1's all over the place. It's here, it's here, it's here, it's here, it's here. This is simple enough. In this case, you could probably see the blue coloring that shows that arg1 there wasn't declared as I've misnamed it in this function, and that's where the failure is. But now we have this source feedback that shows me the exact line of code, the compilation that it was trying to do on that, the stack trace of how we got there. It's called from my2, which was called from a pure function. And if we want to drill into that, we can see how that function was called. But if this was 1,000 lines of code, being able to say the exact point of failure and reason for failure is now really great for debugging. And if we're using typing as a way of writing bulletproof code that's guaranteed to work, then we might be using typing exactly to find that error and not have the typical Wolfram language compiler operation when things go wrong is to fall back to the interpreted version and try and muddle through. And we've also added some functionality to control that more precisely. So now we can say, if things go wrong in the compilation, don't try and fall back to calling the Wolfram engine and muddling through, fail. And if we want guaranteed correctness, that's a better behavior. If we want things to work more often, then the default action of making a callback to something that is executable in the Wolfram language means your code is likely to run, but it may not be fully compiled, so it's not as fast as it could be. One last topic, and how are we doing for time? We still have a bit of time, so let me talk about external objects. Again, a bit of a specialized thing, but if you are working in multiple language environments, this kind of thing matters. For a long time, we've had the ability to connect to other languages. Recently, we made managed environments of that much easier. So here I can say, I want to start an external session in Python, but I don't want just regular Python. I have some external dependencies. So I've got a library called chess. I want you to go in and download and install that and declare it as an import into my session. And that all just happened automatically. That piece of code should just run when you send it to your system. Even if you don't have Python installed, that will just work. It'll just take longer the first time as it fetches these things. And we can call that session and say, in that session, work out 2 + 2 in Python, and we get the answer back 4. Now, where possible, we kind of want these things to be interchangeable. This 4, we know what 4 means. So Python worked out a Python 4, but we want to be able to make use of this. So this thing comes back as a Wolfram language 4, so I can continue to work with it. That's fine for atomic things like integers, reals, and strings. But if you've built some elaborate object in some library, like this chess library, there's an elaborate object that represents an ongoing game of chess. We don't have much use for bringing that back into the Wolfram language. We could try and convert that into some kind of list of associations and links to callbacks, but it's really not much use unless we're going to write an emulator for that object within the language, which is defeating the point of using libraries that somebody else has written. So now with the idea of we can evaluate this with one of its native methods, and it's generated that elaborate object. But what we've got back is an object that allows us to talk about that object in the Python half of the world without importing it. So it's got various information like whether it's got methods and classes, and we can talk about that thing and automate the process of calling Python to do it. So I could ask it some properties. That thing has a method called full move number. We're on the first move of a game. It has methods like a transformational method that says push a piece to E4. And now if I run that full move number, I ended up, oh, sorry, this is a different object now that represents the transformed object that represents the previous object, I think. We can call specific methods on it that will convert back to things we recognize, like plot that board. And there is the board that we created with the transformed piece. Maybe I'm actually still on move number 1 because I haven't terminated the move. So being able to work with more complex external libraries in a way that is controllable much more fully from within the Wolfram language makes these external libraries actually just much more interchangeably useful before you have to say, I'm just going to have to switch back to Python, write a wrapper, and call that wrapper library from within Wolfram language. And this is, at the moment, there's only a couple of languages we support for external evaluation, but this is a new paradigm we're trying to roll out across other external languages that we can talk about. There's a few incremental language improvements. I'll just mention them in passing. Some of these all and any type functions, which are efficient list testing, that we're just filling out that space, and operator forms that are being added. But I'm out of time, so I'm going to wrap here and see if there are any questions. So that's been quite rushed because there's a lot here. It's across all fields. So what we've seen here is audio and video and geometry and calculus and dates and biology and astronomy and programming and some other things that were in that list. There's perhaps the most interesting or exciting are the generative AI and machine learning because they're buzz topics at the moment, but really they're just more bits of computation in our world. There's a whole bunch of notebook improvements, but particularly in code development and using the notebook as an environment for persona delivery in a kind of interactive chat mode, and the other main mode being in it as an assessment platform. And a lot of joining up to make sure things just work, which, in the end are the things that drive you mad in complex systems, when you have to dig down the document and say, oh, sorry, you have to convert this integer to a real for this function to work. We're trying to make those things just work whenever possible. And you've seen quite a bit of that here in this release. So I hope that's been interesting. It's always a pleasure to show off new features. I'm just going to try and get here now the chat and see what questions. I know we've got people on the chat who may have answered some of them as we've gone here. So does semantic search index capture grammatical relations of a language similar to the embeddings of an ANN? Yeah, so basically what that does, semantic search is doing a kind of automated version of what I did by hand here, which is that there is a process by which a kind of semantic neural net that's been trained on real world data is chosen automatically and applied to that. And I believe there are some details for semantic search where I can override that and say, no, I want to use a model that's been trained on medical data because that's my context. And it's trying to capture that whole sentence relationship. And you'll notice that when I ran this here and when I ran it here, that the number of sources doesn't match the number of elements. So it's doing, some of my writing notebooks might be 30 pages long, and they're broken down effectively into paragraph type chunks. So out of the 255 notebooks it indexed, it found 27,000 chunks of data. So you're not trying to sum up the whole document in one go. If you've got a document that talks about one topic at the beginning and another topic at the end, both will end up with an index match that will be found in the search. Okay, questions being pasted over from YouTube. Okay, so so the documentation says an external account is needed for processing to be offloaded onto another service. There's several ways we could do this. One is the the kind of the super automatic way, which we've built in, which is, I forget the syntax, but I think all I need to do is do cloud deploy of that answer 26, which was my index that I created, and that will copy the index into the cloud, and then I can do semantic search of, and instead of giving an index object, I can give the cloud object. And by default here, it's going to be private to me, so I have to be signed in. So for this feature to work, you need a cloud account. We do have free cloud accounts that you can use, but they have a limitation that the deployments delete after a month from the free accounts. We are moving over, I think this year we started moving over to all new licenses, and new site licenses are getting cloud accounts as part of their subscription automatically. So if you have any kind of subscription going forward, there's maybe some of you on a legacy that hasn't quite renewed, but going forward, anyone who's on an active subscription gets a cloud account that doesn't auto delete. And then the other thing you can do is you can use things like the Wolfram Engine and the Wolfram Web Engine tools to set up a service on your own servers that basically wraps this in an API function, and that will let it be callable from elsewhere. So this isn't too much of a barrier, but yes, if you don't have any kind of subscription and you want it to work out of the box, then you need to create a free account that will at least give you temporary ways of deploying these things. If they're deployed by somebody else and their permissions have been set to public or to allow your login to use them, then you'll be able to use them just by if they're public, you'll be able to use them without having to have any kind of account. And if they are limited to, if you've been named as a named user, you need to have a cloud account, but it doesn't need to have any kind of active subscription. You just need to have a Wolfram ID. So quite a few corner cases to that. Let's look at the next question. So can educational features be exported or accessed via browser on machines, smartphones that do not have Wolfram software installed? So again, several answers that. The question object that I showed there, if you use cloud notebooks, so you're running them in the Wolfram cloud, then you can access them through a browser without having to have any Wolfram software. So that would be, you would as a deployer would need a Wolfram account, but the user would not need to, that you could set them as public accessible things. The Wolfram e-learning platform also provides a mechanism that implements some of those things directly in JavaScript HTML. So it has a means of deployment that is pure web technologies. Not all of these things supported. That's an emerging platform. And then there are things you can do, for example, using Wolfram Web Engine, Wolfram Application Server to deploy APIs that use things like the all of the functionality, but probably not the interface parts if you're using them as API functions, but things like the scoring function, whose name I've suddenly gone blank on, the assessment function. The assessment function you could put on an API and serve off your own servers, and then have your own apps or your own HTML, JavaScript, React type front ends on it. So we've got everything's componentizable, but out of the box, the things I'm showing need some Wolfram technology. Okay, so I'm sorry, Ronnie's got a complicated question about time references on the astronomical dates, and it's not a field I know the details of, so perhaps we can take that question and answer it offline from somebody who's on the monitoring team here. Jamie can answer the question in a moment of what the webinar series is, because all of these things I've talked about, the actual developers who built them are coming over in the next few weeks and doing more than the one-liner. You'll get some real behind-the-scenes depth on some of these functions, but there's so many that I've had to dot through them very fast here today. Next question. Okay, sorry, David, your question on specialized machine learning networks, again, is outside of my expertise. So operations on regions, there aren't, I believe, any new operations on regions. I think there were a couple of efficiency improvements in some, but the main thing is that you can operate on these colored regions, and the computational features will ignore the coloring, but will preserve it through if you're spitting out a region. So I don't think there are any new region computations other than this ability to declare regions in a symbolically polar way. Will Wolf interact with compiled languages like Go and C? Yes, so there are some very rich mechanisms, particularly for C, for being able to link into external DLLs, external libraries. We have things like C++ native types that you can use to pass data backwards and forwards. The compiler functionality can do that within the compiler as well, so you can compile Wolfram language code so that it then interacts directly with CDLLs. We don't have anything out of the box at the moment for Go, so your route for Go is likely to be to write a kind of C wrapper or C++ wrapper around Go to kind of bridge the layer. I know there is some code buried if you examine the internal functionality of semantic import is actually partially implemented in Go. So there are some tools if you look through the definitions behind the scenes on semantic import for calling Go, but I'm not sure it's a template I would recommend you go to. So C++ and C, yes, really well covered. Go, not so much. We're running out of questions that I have answers to on the chat. So we're also running out of time for what we allotted. So let's give a moment to see if there's any last questions you'd like to add into the chat. The two I know that are still answered there will get you answers offline from somebody who knows the answer. But if there are no further questions, then let me thank you all for your patience, and hope you enjoy using Wolfram language.
Thank you, John. That was fantastic.
To sign off. Thank you very much.
Thanks so much, John. This is Jamie again. I just want to thank everybody who's here behind the scenes answering questions. We did do a good job keeping up with those. Thank you. And we will follow up with those as promised. Let me share my screen here for a second. And next week's webinar, next Wednesday, is mathematical computation in version 14.1. And that brings Devendra Kapadia and his team of calculus and algebra developers. Will be talking about symbolic arrays in their calculus, stability analysis of dynamical systems, and advances in PDE modeling. And Devendra will also give us an overview of the latest mathematical functionality. So that will be a pleasure to hear from them. We hope that we will see you next week. Thank you, everybody, for your attention today, and we'll see you soon.